Alright, okay, so I kind of gave you a bit of context there. So I said, right, this is how we can describe transformations using matrices. And specifically, if I give you any shape you like, I can describe that that transformation, simply by thinking about where I and j end up after applying that transformation. Okay? So, let's actually try and formalise this a little bit, because I realise I gave it to you in context. Now I need to try and break it down a little bit. So let's suppose I start from the perspective of, this is the transformation I want to apply. What would the transformation matrix be? Okay, so I'm going to draw my transformation matrix in. And what I'm going to do, just to illustrate this is before I've applied any transformation. Okay, so I is here and j is here. And I is 1, 0 and j is 0, 1. Just like before. This is before any transformation has been applied. Then what I want to do is say, right, if I do this transformation, what is the new transformation matrix? In other words, where does I and j end up after I've applied that transformation? So for example, let's suppose the transformation is going to be a rotation. It's going to be a rotation by 90 degrees, let's say anti-clockwise. So in other words, in that direction. So anti-clockwise. Okay? My question is, what is the transformation matrix that would give me that transformation? Okay? So all I need to do is think about where I and j would end up after I've applied that transformation. So where would I and j end up after I've applied that transformation? So where would I end up?
0, 1.
Yeah, good. So I has gone like that. Okay, it's been rotated 90 degrees anti-clockwise. Do you see that? Okay, so I ends up here. Okay, and where does j end up?
-1, 0.
Fantastic. So j ends up down here because it's been rotated 90 degrees anti-clockwise. So j ends up down there. Do you see that? Okay. So in which case then my transformation matrix, remember I put I first and then j, would just be the relevant positions of I and j. So I has ended up, as Samara quite rightly said, at 0, 1. So I put 0, 1 there. Remember I write it as a column. And j ends up at -1, 0. And remember I put that in as a column. Okay. So what I've done here is I have produced a transformation matrix which corresponds to a rotation of 90 degrees anti-clockwise. Is that okay? So in other words, I could take any shape I like, work out its coordinate matrix just by putting them in as columns, multiply that coordinate matrix by this, and it would tell me where the new coordinates would end up, which correspond to a rotation 90 degrees anti-clockwise. Is that okay to everyone? Yeah? In fact, I can show you on here then. So a rotation 90 degrees anti-clockwise would mean that that ends up over here, and that ends up here. Okay? So I've literally just rotated the entire thing round by 90 degrees anti-clockwise. This would be the transformation matrix. Okay. Let's do another one then. Let's do another one. So get rid of that. Replace this. I'll cut with a new one. So let's suppose instead then, I didn't want to do a rotation. Let's suppose I'm going to do a stretch. Okay? So let's suppose I'll go for a stretch. And let's suppose the stretch is going to be a scale factor of 3. So a scale factor of 3. So what that means is that I'm stretching every single direction by 3. Okay? So what I'm going to do is I'm going to draw my new coordinate grid out. So this is x, this is y, and this is the origin. And then all I need to do is just tell me where I and j is going to end up after I stretch the entire plane by a scale factor of 3. So where would I end up if I stretch it by a scale factor of 3? 3, 0, right? So instead of being there, it's going to be 3 times as long, way out here. That's new I, okay? That's new I, so it'll be at 3, 0. Okay. Where would j end up if I stretch it by a scale factor of 3? 3 times as long, so it was only 1 as long, it's now going to be 3 times as long. So it's going to be way up here somewhere. So that would be j, okay? And that would be at 0, 3. Are you happy with that? Okay. So this would be a stretch scale factor 3. This is the transformation matrix of a stretch which is scale factor 3. Okay. Is that all okay? Yeah? What if I wanted to do a slightly more complicated transformation? Let's go, for example, with, let's go with a reflection. Okay? So let's go with a reflection in the y-axis. Reflection in the y-axis. Okay, direction in the y-axis. All I need to do is just think about where I and j end up after I've applied this transformation. Okay, so where would I end up after I've reflected it in the y-axis? So it's my y-axis. If I reflect everything in the y-axis, where does I end up?
Zero.
So after I reflected I in the y-axis, where does it end up? Negative 1, 0, right? It ends up over here. Yeah? A bit better. Is that okay? Is that okay? Right, I've literally taken him and just reflected him over. Where does J end up after I've reflected him in the y-axis? It stays the same, doesn't it? If I reflect that in the y-axis, it stays the same. So J will end up here. Okay, in other words, at 0, 1. So in other words, this matrix here will be the transformation matrix which corresponds with a reflection in the y-axis. So I can basically take my coordinate matrix, wherever it is, and I can multiply it by this, and that will give me the new coordinates, which corresponds to a reflection in the y-axis. Is that okay? Yeah? Let's do one final one then. Do one final one. So let's do something called a shear. So a shear. Now a shear is a bit weird, okay? Because what it basically is, the best way that I can describe it, is it's a stretch in one direction. Okay, so it's a stretch, but in one direction. So it's almost like a diagonal movement, right? So let's suppose that we're going to shear it by a scale factor of 2. Okay, but the line which doesn't change is going to be the x-axis. So we call that the invariant line. So let's say the x-axis is invariant. It doesn't change. Okay. Now the best way that I can describe this is using this. Okay. So if it's a shear by a scale factor of 2, what that literally means is that I'm taking J and I'm moving him by 2. Okay, I'm moving him by 2. So it's a shear by a scale factor of 2. I should say in the x direction. So in x direction. Okay. So it's shear by a scale factor of 2. So I'm picking him up and I'm moving him by 2 in that direction. The x-axis doesn't change. All right. So let's think about this. 0. Right, okay. So here is what a shear would look like. So a shear would basically be like that. Do you see that on the screen? Yeah? So I basically picked up this and I've moved him in that direction there. Moved him in that direction there. So it was there, and now it's kind of diagonal. It's moved diagonally. Alright? So what's happened here is that J has moved to here. Okay, so J has moved to this position here. So J will be at 1, 1. And I, let's say that I hasn't moved, so I will remain down there. So I will still be at 1, 0. Okay? So effectively what this is, you notice that instead of having like a variation of 0s and 1s now, I've effectively stretched it in that direction. Okay, so I've got this kind of shear going on. It's basically diagonally. It's basically diagonal. Is that okay? Yeah? So it's a weird transformation. It's something that looks like this. Okay. Now, to be honest with you, I wanted just to show you that one for completeness. If you didn't understand that one, that's fine. Okay, it's not actually on the syllabus, but I wanted to show you it for completeness. Because, like, why can't we have stuff like this going on? There's basically a 1, 1 now. What that means is that J has kind of moved in that direction, which means that we call that transformation a shear. All right? But can you have a look at question 5 then? Can you have a look at question 5? And if you feel happy with those, have a look at question 5b as well. Let's have a look at question 5a. I've given you a list of transformations. Again, don't worry about 5, but do 1, 2, 3, and 4. See if you can come up with the transformation matrices.